see. Let me know if you can see that.
Yes.
Great. So yeah, I'll get started. So as Mark said, I'm Emily, and I met Mark in Chicago when he gave a talk here on quantum cryptography. So I'm glad now that I'm able to give a talk for him on post-quantum cryptography. And let's get started. So just a little bit about me. Senior consultant in quantum computing at Protiviti and co-founder of CSNP, or cybersecurity nonprofit, which provides free security educational resources. Previously, I was a research security engineer specializing in cryptography, so hence the cryptography presentation. And before that, I was a mathematics researcher, which is really what got me into cryptography. So the agenda for today, first, I'll just start with the basics of what is cryptography, what is good cryptography, and an overview. Then I'll very briefly talk about what is quantum computing and its effect on cryptography, and also what is quantum cryptography. Then I'll talk about post-quantum cryptography, the NIST competition, how you create post-quantum cryptography, and where we are today. And finally, this will be the main portion of the talk. We'll get into the mathematics. So I'll talk about lattice-based cryptography primarily, as it's the most popular type of post-quantum crypto. Then I'll talk a little bit also about code-based and briefly touch on multivariate. And then I'll talk about hash-based, and it's a little bit about its use in cryptocurrencies. And finally, if there's time, I might touch on isogeny-based. And then have the conclusion. So first, an introduction to cryptography. So I like to start all the way at the beginning with what is cryptography. So cryptography, from the Greek kryptos, meaning hidden or secret, and graphen, meaning to write, literally translates to secret writing. So from the Caesar shift 2,000 years ago, which was just shifting each letter over by a certain amount, to the Lorenz cipher machine used in World War II, to today, where cryptography is used to mean secure communication in the presence of third parties. So cryptography today has three main components. The first is confidentiality, so restricting the access of information. And that's pretty similar to why cryptography was originally created as well. If even thinking back to the Caesar shift, it was about shifting everything over so that other people couldn't read the message. But today, we also use cryptography for integrity and authentication. So integrity, verifying that data hasn't been altered in transit, and authentication, verifying the identity of a party. And even maybe 100, 200 years ago, this wasn't necessary. You usually knew who was delivering your information, and you knew that it hadn't been altered. But today, obviously, that's usually not even the case. So these are very important aspects today. And there are three main types of cryptography. The first is public key cryptography, and the second is secret key cryptography, and the third is cryptographic hashing. So today we're going to focus on the public key cryptography. So we talked about what is cryptography, but what is good cryptography? So I think good cryptography relies on three main components. The first is the key secrecy. So in most cryptographic algorithms, you have a key, which is a secret piece of information that's used to uncover or reveal other information. And key secrecy might sound very obvious, but it's actually a very difficult part when you get into especially large organizations using key management, rotating keys, making sure only the correct people have access to them. Key secrecy is actually a very critical component. The next is hard math problems. So usually the strength of the cryptography relies on the hardness of some underlying math problem. And if you can solve that math problem, you can break the cryptography. And finally, proper implementations. The algorithms have to be correctly implemented to not leak information. And this is also something that gets overlooked, but it really is critical because even a very slight information leak that might not even seem like a leak at all, like returning whether or not the padding went through, things like that, that don't even seem like you're leaking anything, can actually be used to completely destroy the cryptography. So that's really important as well. And generally, like the hard math problems isn't where people go to attack cryptography because there's so much research and work into making those very strong. But today, actually, we are going to be talking about basically solving these hard math problems, and that's how breaking the cryptography. So we're going to focus on public key cryptography today. So with public key cryptography, you have a public key that's known to everyone, and then a private key that's only known to certain people. And there's three main types. There's the asymmetric encryption, key exchange, which oftentimes goes with asymmetric encryption, and digital signatures. So encryption or key exchange is where you take some text, you encrypt it into some scrambled data that you can't make out, and then you decrypt it to the original text. And so the public key is used to encrypt and the private key is used to decrypt. And this provides confidentiality, and it's often used in key exchanges, so creating a shared key among multiple parties. And the reason is this cryptography is only one way. So whoever encrypted with the public key, they can't actually decrypt. They can't even decrypt their own message that they sent. So for that reason, usually this is just used at the beginning to get a shared key, and then symmetric encryption is used. And some examples include RSA, Diffie-Hellman, and elliptic curve cryptography. And then the digital signature type is you use a private key to sign and a public key to verify. And this provides authentication and integrity. So some examples include RSA, DSA, and elliptic curve digital signature. And you can see here using the private key to sign, using the public key to verify. And also it's important to note, if you're ever wondering which one is used to sign or verify, encrypt or decrypt, the private key is always used for the more sensitive operation. So you want only certain people to be able to sign. You only want certain people to be able to decrypt and read your message. So those actions use the private key. So where is public key cryptography used? It's used all over the place. Basically, anytime two or more parties need to communicate, that's really what public key cryptography is about. It's really about communication, secure communication. And parties aren't necessarily people. And a great example of this is HTTPS. So the S stands for secure, and it means that the traffic is encrypted. It means that you've authenticated the server, so you know who you're talking to. And you also know that the data getting sent back and forth isn't getting altered. All right, so now that we've gone over what cryptography is, I'll start in with quantum computing. So a quantum computer is a computer that's based on quantum physics rather than classical physics. So instead of using the bit, which can be 0 or 1, it uses a qubit, which can be any combination of 0 or 1, more formally, any complex linear combination. And it takes advantage of certain quantum phenomena to perform some tasks much more efficiently. So the effect on cryptography, the main effect it's had on cryptography is that Shor's algorithm is an algorithm that can factor efficiently. And factoring is the hard math problem that RSA relies on. So it also has similar algorithms that can actually attack all the different public key cryptography we have now, because it's actually, they're all instances of the same more general problem called the abelian hidden subgroup problem. So we have this algorithm that can solve these problems we thought were hard, and they are hard for our current computers, but we can solve them efficiently with quantum computers. So even though we don't have a quantum computer large enough yet to run this algorithm, it's a very clear threat to cryptography and shows that eventually all of our public key cryptography will be obsolete. So I also wanted to briefly touch on quantum cryptography because a lot of times quantum, post-quantum get mixed up, but quantum cryptography is cryptography that's based on quantum physics. So quantum is the problem, it's also the solution. It's kind of used as offense or defense in a sense. So one example is the quantum key distribution. And so quantum cryptography has security like no other form of cryptography because it's actually secured by the laws of quantum mechanics. The problem is that quantum cryptography has a lot of different reasons why it's impractical, especially for certain use cases. And for that reason, the solution is post-quantum cryptography. So post-quantum cryptography is cryptography that runs on our current computers, but it's secure against classical and quantum attacks. So it's just like RSA, it's just like all of these other cryptography algorithms that we already use. It's just based on harder math problems. All right, so now I'll talk about post-quantum cryptography. So NIST is currently having a competition to determine the new post-quantum cryptography. So it's a really exciting time for cryptography. They're really at the final stages of determining it. But first I wanted to talk about how you actually create post-quantum cryptography. So the first step is you have to identify the hardness assumptions that are not broken by quantum computers. So we assume that factoring was hard, and that's true for classical, but clearly that's not true for quantum. So we need to figure out which problems we can use that will still be hard for quantum computers. Once we have identified those problems, we can build crypto systems based off of them. And this is also hard to do because, for one, it's not all problems are, even if they're hard, they're not necessarily good for cryptography. So for one part, a lot of times good problems for cryptography are hard to solve in one direction, but easy to solve in the other. But more than that, you have to think about, will your crypto system be efficient? Will it have small key sizes? Will it be fast? Will it be easy enough to implement or scale? So there's a lot to think about even beyond just finding a hard problem. And then you have to prove the security against quantum and classical attacks. And so this is also very hard, especially since public key, post-quantum cryptography and all of our cryptography that's runs on classical computers, we don't have absolute security proofs in the same way that we do for quantum cryptography. But what we can do is we can show that breaking these crypto systems is as hard as solving another problem that we know to be very hard, even NP hard at times. And so these security proofs are really important. And for our current cryptography, we didn't have security proofs like this. So even though it doesn't have that same, I guess, absolute aspect that quantum cryptography does, it's still very, very, very secure, a very good proof. So I mentioned that we don't have a quantum computer now that can break our cryptography, which is good. But why should we switch to post-quantum cryptography now? So I have listed some reasons why. The first is it works on our current computers. So you can already, a lot of it's open source too. You can already go check it out, implement it, try it out. It works just fine. The second is that it's more secure against quantum and classical attacks. And also it's hard to estimate when a quantum threat will occur. So there's a lot of reasons for this. First, it's a completely new science and technology. So it's a lot harder to predict. We don't know when there will be a breakthrough. We just know that we need to have this cryptography in place before that happens. And it's also hard because it has such a implication on security that it's possible a lot of governments won't release all of the details, especially if they can create a quantum computer that can break our cryptography. That gives them a clear advantage. So that's another reason why it's hard. So we just know that we need to get this in place before it happens. And also, attackers are already storing encrypted data for later. So that's something also to think about. If the data is going to be relevant long term, then it's more important that we use post-quantum cryptography as soon as possible. But if it's something like credit card numbers, then maybe we don't have to worry about that yet. The fifth is that transition in cryptography takes many, many years, especially at large organizations. It can take a decade just to increase the key sizes across if all the different applications, for example. So we really do need to give everyone a lot of time to make this transition. And there are some implementations that might not be able to switch cryptography in time, or that it might be really impractical to go back and switch it. And finally, government agencies have already announced that they plan to switch to post-quantum cryptography based on the NIST results. So this is what the NIST competition looked like in round 2. Here I have the different types, so encryption and key exchanges here and signatures here. And then I have it by the different math problems it's based on. So lattice code, multivariate hash, and isogeny. And so there were 26 algorithms left. And then in the summer of last year, NIST narrowed it down even further to some round 3 finalists. And so now we're only down to 7 algorithms, and most of them are lattice, which is really exciting, especially if you're a fan of lattice cryptography. So this is what we have remaining, but a lot of the hash algorithms and the isogeny-based algorithms, they still have importance, and they're still alternate candidates. So even though they're not for now in these finalists, that doesn't mean they'll never be used. So I think it's also important to talk a little bit about them. All right, so now I'll talk about lattice-based cryptography. So this is cryptography that's based off of hard lattice problems. And the first encryption scheme was proposed in 1996 and true by 3 professors at Brown. And lattice really from, I think the whole competition has been leading in terms of the most schemes. And then of course, definitely by the end. And it's also one of the, well, now it's the only type. And I think in round 2 as well, it was the only type of math problem that had both encryption and signatures remaining. So it's very versatile. It's also being used for a lot of other cool things like fully homomorphic encryption, which allows you to do computation on encrypted data. And it's very efficient. It's very adaptable. You can also show that the schemes are very secure, some as secure as worst case lattice problems. And the only, I would say the main con with lattice is the very large key sizes. So what is a lattice? So you can think of a lattice as a grid. And this grid could be in any dimension. So here we have a lattice, and it's basically a 2-dimensional grid. Back here is a 3-dimensional lattice. And then of course it can go on to hundreds, which is really hard to visualize. So a lattice is formed by taking n linearly independent vectors, so vectors that can't be written as combinations of each other, and then taking integer linear combinations of those vectors. And then you say that this set of vectors is a basis for the lattice, so it generates it. So here you can see this lattice, and here is a basis. And this probably looks familiar in terms of kind of looks like X and Y axis. And all of these points can be created by adding and subtracting combinations of these 2 vectors. So that's a basis for this lattice. But you also over here have another basis, and this basis is also totally fine. It also generates the same lattice. But you can see that it doesn't look as friendly as this one. And that kind of gives the idea of a good versus a bad basis. So you have here this nice basis with short vectors and they're perpendicular. And over here, not so nice, longer vectors and they're not perpendicular. So now that we've defined what lattices are, let's talk about some of the hard lattice problems. So one of the most famous, I guess, hard lattice problem is the shortest vector problem. So given a basis for the lattice, you have to find the shortest non-zero vector in the lattice. And if we go back here and we try to solve this problem, given this basis, we can see that's very easy. In fact, the shortest vector is actually given as part of the basis. But here that's a little bit harder because it's not given as part of the basis. But for a bad basis, this problem is NP hard. And even if this problem doesn't look that hard in 2 dimensions, remember it would be in hundreds of dimensions, so it very quickly gets very hard. And a generalization of this would be the approximate shortest vector problem. So pretty much the same thing, given a basis for a lattice, you find a vector that is at most a times the length of the shortest vector. So if a was 2, it'd be, you could find a vector that is at most twice the length of the shortest, and that still solves the problem, although a would probably be much smaller. But those are some hard lattice problems, and there's a lot of other problems that are very similar or related and really important in cryptography, but SVP is definitely one of them. So now I'll discuss what learning with errors is, and learning with errors is probably the most important problem in lattice-based cryptography. Most of the schemes that are remaining are based off of learning with errors, or one of the variants that I'll talk about in a minute. But what is learning with errors? So how it works is first you choose a secret vector S and a prime Q, and then you're going to iteratively from 1 to m choose vector AI and some small error EI, so a small number E and a vector A. Then you're going to compute BI, which is the inner product of AI and S divided by Q plus that error. And then the learning with errors search problem is, given m pairs of AI and BI, find the secret vector S. And this can be shown that it's at least as hard as SVP variants and related problems. So depends on the parameters you choose, but learning with errors can be NP hard. So that's a very good sign for cryptography. And a couple important variants. So ring learning with errors is very popular. Basically, instead of using solving these equations, it's more like you're using polynomials instead. So it's pretty much the same idea, but with polynomials. And I should go back and say too, so learning with errors can be reframed in a lot of different ways. And you could look at it as matrices. You can reframe it as a lattice problem. You can also just think of it as solving a system of linear equations, which is very easy to do, but now with some error, hence the learning with error. So ring learning with errors is similar, but using polynomials. And the reason you would want to have this ring structure is usually because of efficiency. You can get away with smaller key sizes. And similar with module learning with errors, it's really just a different structure using a module, which is essentially a vector space, but for the elements are in rings instead of fields, if that's something that's interesting. But really, you can think of it as just another structure that, again, the primary reason is to increase the efficiency. And there's another variant called learning with rounding. Instead of using that small error to kind of hide the secret, you deterministically round. And learning with rounding, also you can do it with rings or modules. So those are some of the variants, but the idea itself of learning with errors is really fundamental for lattice-based cryptography. So now I'll show what the LWE lattice scheme would look like. So first you have Alice, who does the key generation. So that's pretty much what I went over. She chooses her secret vector S, and then she computes all these pairs AI and BI. She keeps S as her private key, and then she sends the public key, these pairs, to Bob. Now Bob has a bit X that could be 0 or 1, and he wants to send that bit to Alice. So he's going to encrypt it. And how he does that is he sums over some subset of the AIs and BIs, and he gets A and B. But with B, he also adds his bit over 2. So now he can send this A-B pair to Alice. So Alice has A and B now, and she needs to figure out if the bit was 0 or 1. So basically, she just undoes this equation, and she won't be able to tell exactly, she won't get an exact number because she doesn't actually know what the error is. So even though Alice generated all of these pairs and the error, she doesn't know what subset Bob summed over, so therefore she doesn't know the error. But she knows that she chose the error to be small enough so that by undoing this equation, if she gets less than a fourth, she can determine that the bit must have been 0. But if she gets more than a fourth, she can determine it must have been 1. So that's how Alice decrypts. And then if you have some eavesdropper, Eve, trying to recover S, she would have to solve an NP-hard problem to do that. Because again, she doesn't know S, she doesn't know the error. It's just very hard to get that information back. So these are the lattice schemes remaining. We have in gray the ones that were removed. So all of these are from round 2. The last 3 are the signatures, and the first ones are the encryption. And then in green, we have the ones that are remaining in the final round. So we have Entru, Kyber, and Saber for encryption, and Dilithium and Falcon for signatures. And again, can kind of see the ring module, the different learning with error, learning with rounding, all coming back. So it really is very important. Okay. So now we can talk about code-based cryptography. So code-based cryptography is cryptography that's based on error-correcting codes, which are maps that correct an error. And this was first invented by McAleese in 1978, but it didn't really receive a lot of attention because RSA had just come out, I think in 77. So RSA was much faster, it had much smaller key sizes, and it was also just easier to understand. So there wasn't really a lot of attention for the code-based cryptography until RSA we found was vulnerable to quantum attacks. That's when we started to look at code-based cryptography again. And also because at the time, the key sizes in code-based cryptography were pretty much just impossible. Now they're still very large, but they're not impossible. We can do code-based cryptography. So it's primarily used for encryption, and all of these algorithms were from round 2 for encryption, and there's one remaining in the third round for encryption, and that's the classic algorithm. And there's one of the main pros, I think, for code base is that its hardness is well studied and well understood for over 40 years. So that's really important when looking at cryptography. It's the oldest form of post-quantum cryptography, I believe. So that's really beneficial because you want something that's been studied for a very long time. So it's all about error correcting codes. So sending an input plus some small error back to itself or correcting the error. So I'll talk about the scheme. So first, for key generation, you choose a linear code that corrects T errors, and you choose its generator matrix G, and you get its decoding algorithm A. So then you're going to choose a few other matrices. You choose a matrix S to scramble and P to permute or reorder. And then you can compute this G prime, which is G sandwiched between S and P. And so basically it's hiding that generator G. So the public key then will be G prime, kind of that generator that's hidden, and T, which is the number of errors. So that's what everyone needs to know. And the private key are these matrices used to scramble and permute S and P, and then the generator G and decoding algorithm A. So this is how the scheme works for encryption. So Alice generates the keys, pretty much as I just said, with the G prime T being the public key that she sends to Bob. And now Bob has a message vector M, which he makes into a binary vector. And to encrypt, he creates an error vector E, which just is all zeros with T ones. And then he encrypts by doing matrix multiplication of M times G prime plus the error E, and he sends that ciphertext to Alice. Now Alice can decrypt it, so she applies the permutation matrix P's inverse, which gives MSG here plus EP inverse, and EP inverse is just some other error. So she can then apply A to decode it and just get MSG, and apply inverses to recover the message M. So Eve would have to be able to decode the general linear code, which is an NP-hard problem. All right, so that was code-based, and now multivariate I'll just briefly touch on. Multivariate is polynomial equations in multiple variables, and it's primarily used for signatures. And it's basically just conceptually a little bit easier because it's one function in one way to encrypt, and then being able to break that function apart and invert it to decrypt. And so in the final round, it has Rainbow as its last remaining algorithm. So Rainbow is the non-lattice digital signature algorithm. And next, hash-based. So hash-based cryptography is based off of hash functions. So there's something called a one-time hash signature, which allows you to sign something once. But of course, we want our signatures, we want to be able to sign many times. So you can combine them with Merkle trees, which basically allow you to chain these hashes. And by concatenating all the hashes, you turn this one public key, you make it able to sign and verify many different one-time hashes. So basically the scheme is using Merkle trees to allow you to do a one-time hash signature many times. And its security is very good. It's only based on the security of the hash function. And in most cryptographic protocols, you generally need to have a secure hash function anyway. So that's all that it needs, is that's the only security requirement, which is really great. And also it's very easy to just switch that hash algorithm out as well if it is broken. And there aren't any finalists for the NIST competition, although Picnic and Sphinx are still alternates. But I did want to mention that it is useful in blockchain and crypto. There's something called a stateful signature, which keeps track of, you have to keep track of the state. So basically the index of where you are, for instance, on the Merkle tree. And that is not really good for most signature schemes. That poses a lot of practicality and security potentially issues. But for blockchain, this actually is fine because blockchain has to keep track of things in this permanent way anyway. So there are some stateful signatures that have already been standardized, and one of them, XMSS, which is Extended Merkle Signature Scheme, is being used right now for the quantum resistant ledger. So that's also something to check out. Hash cryptography is being used, even though it's not going to be probably the chosen algorithm for the NIST competition. And so lastly, isogeny-based cryptography, which I'm not going to go into too much detail on, but basically it's all about maps between elliptic curves. And of all the cryptography, isogeny-based cryptography is definitely, it's the newest form, and it's the least understood as well, I would say. And there's some advantages, like it can have very small key sizes, but there still need to understand the hardness better, and it can be slower than other candidates. But it is really an interesting type of cryptography, and it's all about isogenies, which are maps between elliptic curves. So in elliptic curves, it's the same elliptic curves that are used for our current elliptic curve cryptography, but now we're looking at these maps between them that preserve some of their structure. And so I'm going to end there. So some conclusions. We talked about how cryptography ensures secure communication in the presence of third parties through difficult math problems. And we explained that quantum computer is a computer that's based off of quantum mechanics, and quantum algorithms like Shor's algorithm and other variants can break our current cryptography. But post-quantum cryptography runs on our current computers and is believed to be secure against quantum and classical computers. And then we went over the different types. So lattice-based cryptography, the primary algorithm for that is learning with errors. And lattice-based is good for encryption, signatures, as well as many other types of schemes. And then code-based cryptography, which is for encryption, is based off of error correcting codes. And multivariate cryptography, which is for signatures, is based off of equations in multiple variables. And hash-based cryptography, again for signatures, which is using hash functions and Merkle trees. And then finally, isogeny-based cryptography is used for encryption or key exchange, and it's all about maps between elliptic curves. All right, so thank you. I'll now take any questions anyone has.
Fantastic. Thank you so much, Emily. That was really, really great. Does anyone have any questions? Okay, I have some questions. So what are your personal favorites in the NIST competition? What do you think will happen and why?
Oh, definitely the lattice schemes, I think, are the most interesting. Um, I would say the ones based off of the learning with errors, more so than the learning with rounding, I'd say are the more interesting. But yeah, pretty much all of the learning with error, learning with rounding schemes like Saber, I think is very cool. And Crystals to Lithium, Crystals Kyber, those are all very exciting schemes. And then Falcon as well for signatures.
What would you say to someone who listens to this talk and they say, oh, okay, but quantum computers probably won't be able to crack existing encryption for decades or something, and so why do I need to fuss with all of these post-quantum encryption algorithms?
Yeah, so I would go back to my slide about why you should do that. I think there's so many reasons, but just highlighting that we don't know when the threat will occur. We need to be prepared before the threat. We need a lot of time to actually implement these crypto systems. We definitely don't want to be rushed doing this either. Those are some reasons off the top of my head.
Good. So a related question from Barry Bird is there a timeline for the switchover to post-quantum? Do groups know when they should be doing this? Is there an agenda either for the government or corporations on when they should begin?
Yeah, so I think people are, if they're not already trying it out, they're planning on switching over as soon as NIST finalizes. And I think this competition could be over in a year or two, but also it's pretty well narrowed down to these few algorithms. So what companies can start doing already is planning out how they're going to do this transition and who's going to do it, what's their timeline look, and kind of assuming that the actual algorithm will be decided in a year or two. But of course, they can also start preparing to be more crypto agile, which means able to switch crypto systems very easily. So I would say that's like a main thing that they can do. And again, there's only 7 algorithms left, 4 encryption, 3 signature. So that's not too many, can already start implementing those.
Good. So there's a question from Chandler Watson. How come the lattice-based NIST candidates often seem to integrate LWR, like Sabre dilithium? Is it just for computational efficiency?
And I heard part of that, just the end. Sorry, can you say it a little louder?
Why do the lattice-based NIST candidates seem to integrate LWR, like Sabre and dilithium? Is it just for computational efficiency?
I think efficiency is the main reason, primarily key sizes. Let me go back. So asking why learning with rounding or why the different variants. Learning with rounding versus learning with errors, I'm not really sure if there's a big difference between that, but adding the structure with rings and modules, there's a lot more mathematical structure in that, which means you don't have to specify as much, I guess, and you can use like smaller dimension lattices as well. So I think that's the main reason, is to try to like make the key sizes smaller, but I think it also makes the security proofs more difficult sometimes. So it's not always a good thing. It's kind of a balance between that.
There's actually a question about the key sizes. You mentioned that the key length for Michaelis has decreased from 10,000 or more bits to fewer bits. How has this occurred, and what is the current number of bits needed?
I don't know that it's decreased that much. I think it's more that the computational power has increased. It may have decreased with some of the other schemes, like the classic Michaelis, I think is pretty similar to what it initially was back in the 70s. I think that these other schemes that I think some of them have smaller key sizes, but the issue is more with, the security proofs. As Michaelis is, with so many years of study, that's why it's one of the remaining candidates. That's one of the important things about it. So yeah, I don't know that the key sizes have decreased that much with the remaining Michaelis scheme. It's more just that computers can handle them now.
There's one more question. Will any of the hardness arguments be in trouble if someone discovers that P equals NP? A lot of things will be in trouble if P
Yeah.
equals.
It's very possible. So with the code and lattice, I think some of the others, they're NP hard problems. So technically they might not be in trouble because they're at least as hard as the NPs. So it's possible they won't be. It's also possible that they will be. A lot of things could be bad if that happens. So for lattice and code-based, yes. For hash, I don't think that would matter because hash isn't really, it's kind of a different security proof. In a way, hash-based algorithms, some of them don't even have security proofs in the same way, like the SHAs. So it's possible at any point you could break one of the SHAs, and then you just have to switch it out for a different hash algorithm. So for that, it wouldn't matter. But yes, for the others, it could. For isogenies, yeah, I don't know if it would or not.
Good. Are there any other questions?
Yes, I have one question.
Yes.
What do you think of Monte Carlo based lattice rules? If they can help make this lattice based cryptography stronger with Monte Carlo?
I'm not sure about that.
Okay, thank you.
Yeah. Could you talk a little bit more about it though? I'm interested.
Yeah, I worked on that, so it's interesting.
Oh, very cool. Yeah, I'm actually in like quantum now, so I'm a little bit rusty now on the cryptography side, but obviously still very interested in it. So that's very cool.
So there's one more question. Can you suggest post-quantum algorithms for devices with limited resources, like some measuring instruments?
Yeah, I think that's where isogeny-based cryptography would be a good one because that has the smallest key sizes. So that's good when you're limited resources. But most of the others have pretty large key sizes. So if the isogeny-based cryptography does, right now it's one of the alternates, but it still has the potential to be standardized eventually, even if it's not standardized right away. I think that could be a good one for that. But also probably lattice. Lattice tends to be pretty good for everything.
How is NIST shortlisting the algorithms? How one algorithm is considered better over the others?
Yeah, so I think there's a lot of things that are being taken into consideration. Of course, the main one is security. Right now, all the algorithms are up. You can look at them, people comment on them. That's how I think they started with 60 algorithms or so, and it was very quickly narrowed down and then further narrowed down. So security is one way, is one part. Clearly, if somebody comes up with a way to break or even potentially break the scheme, it might be out. And then once they come down to those 26 schemes, I don't think security was like a huge concern for most of them. So it came down to efficiency, so speed, key sizes, which ones have the best, which have the best, like, which can be most easily implemented. That was another consideration. How well studied the hardness was. So that's why I think isogeny was one of the reasons it was out for the last round, is because it's the newest form. So it just hasn't been studied as much. So those are all some of the reasons. Another one I think is making sure legally that the scheme can be used. I don't know. I heard a little bit about that they were keeping N true in just in case it's patented, and if the Kyber Saber, if those schemes get patented, I think they were keeping it in. So those are all reasons. But at this point, yeah, they're all, I would say most of the remaining algorithms and alternates are all very good.
Super. So thank you again, Emily. That was fantastic, and thank you for sticking around to answer all those questions.
Yeah, thank you so much for having me. And anyone who's interested too, feel free to reach out to me.
Super. Thank you, everyone.